Hello, Professor Haran.
Hi.
Hello, how are you doing?
Fine, how are you?
Doing good, doing good. Nice to see you finally.
Yeah. Would be better to visit in person, but that's the second best, I guess.
Yeah, like when this all gets over, probably we can actually invite you in person sometime.
Yeah.
Yeah.
Okay.
So, okay, so you can, I can make you the presenter now.
Okay, and then I can try to share my screen.
Yes, yes.
Okay, let me do that.
Yeah, I can see this, but if you can make it full screen, yeah, this is
Yeah,
perfect.
there we go.
Yeah, yeah, this is good.
Okay, so everything is fine.
Yeah. So you can keep it like this only.
Okay, fine. We still have some time, I guess.
Yeah, we have like 10 minutes.
Okay. So tell me a little bit what you work on.
Radiation spectroscopy, and also a little bit of biophotonics and nanoplasmonics.
Okay.
That's my work actually. So I joined IIT a year back, and then
Oh, okay.
yes. So I'm building my lab now, setting up my
Mhm.
lab. Yeah. So that's what I'm doing now.
So they treated you well, they gave you enough money to set up a good lab?
Yeah, I got a grant from a government agency here, and also there was a seed grant given by IIT Delhi. So I think I mean if I combine those two, it's quite okay for buying basic equipments and all.
I see.
So yeah, not a lot of money like you get in the US or elsewhere, but it's still okay to build your own instruments. And also we have uh, quite a good central facility here, also departmental instrumental facility, so that we can easily use and have access to. Okay,
I
so
see.
that really helps. Mhm.
Yeah. Uh, And where did you work before you joined IIT Delhi?
Yeah, I was working at the Johns Hopkins University under Professor
Oh,
Ishan Burman. I was working at the Johns Hopkins University in
yeah,
Baltimore under Professor
I see.
Ishan Burman. Yeah. And before that, I was doing my PhD with Professor Chandravas Narayana from JNCSR, Bangalore.
Oh, okay. Yeah, I know
Yeah.
him very well. Yeah.
Uh-huh. So I did my
Yeah.
PhD under him. So,
Okay. Oh, that's cool. Okay. Well, if you talk to him, say hi from me.
yeah, sure,
Yeah, I haven't
definitely.
seen him for a while.
Yeah, he has become a director of an institute in southern part of India recently.
Oh, I didn't know. Okay.
Yeah,
In which city?
I think it is in Trivandrum in Kerala.
I
Uh,
see. Okay.
So happened very recently. I think then he got a little busy with the administrative work and all.
Oh yeah, I'm sure. To be a director is a big work. Yeah,
Yeah, yeah,
yeah.
yeah.
I had a postdoc who worked with him also, Sayan Mondal. You know him?
Yeah, yeah, yeah. I didn't meet him because I didn't have any overlap with him, with Cyan.
Yeah, he probably came after you or something. He worked for a while with Chandra Bas, and then he came to work with me, and now he's in Tel Aviv University.
Okay.
But yeah, but I've met Chandra Bas multiple times, so I know him quite well.
Okay, okay.
Cool.
Professor Pramit is here. Professor Pramit, are you there? Oh, I think he's muted. Okay. So you have been to India, right? You have been to India before? Like,
Multiple times, yes, yes.
oh, okay.
And I actually also visited. I was in IIT Delhi. I can't remember the year exactly, but I came for this yearly fluorescence conference that is run by Sudipta Maiti and other people, and it was jointly between IIT Delhi and um, the university. I forgot the name of the university, the big university in Delhi. Yeah.
Jawaharlal Nehru University, right?
Yes, exactly.
JNU. Yeah.
Uh, Yeah. So yeah, and actually I stayed on IIT Delhi premises, so I got to
Okay.
know the place a little bit. Yeah, it's a very nice campus.
Yeah, that's true. Nice. So you're quite familiar with
Hi, Gilad.
institutes here. Oh, Professor Pramit is here.
Hi, Gilad. How are you?
Fine. How are you?
I'm good. I'm good. Nice to see you after some time.
Yeah, that's true. It's been a while.
So yes,
Yeah.
you were here in 2000, I think 18, where we
I
had
I
this
believe that was the 2018. Yes, the
yes,
fluorescence conference. Yeah.
exactly the same FCS conference, Somik, that you went this time.
Okay, okay.
I mean the last time, the 2019 event.
Yeah. So this time it was virtual, and actually my lab did a lab demonstration, a virtual lab demonstration, which went quite well, I think.
I missed it, Gilad. So you have to demonstrate it for me again.
Yeah, but you know, I told Sumik that the in person is much better than virtual. You know,
That is true.
I really want to start visiting places again. Hopefully
So how is
soon.
the situation out there at your place?
It's not so bad, but it's also not so good. But the government is not handling the situation very well, so it's quite chaotic. I would say we had a big wave, and we are still kind of tapering off from the big wave of Corona in the last month, and we are just opening a big lockdown that we had. So
Okay.
schools, for example, started opening today. Only 20% of school children went back to school, and hopefully the remaining will go over in the next few days. But a large part of the commercial institutions and so on are still closed. The institute here, the Weizmann Institute, is semi-open, so we can work more or less.
Okay.
We are not allowed to be in the lab, all of us at the same time, but we can work more or less. But yeah, it's still a difficult situation. And we have elections in 2 months, actually 1.5 months. And the way our prime minister is trying to do everything to win the election. So I think this is also part of the story. The way he handles the crisis is related to what he wants to get in the elections.
I think, Gilad, it's the same story everywhere.
Yeah, it is. It is. Yeah. Yeah, you
So,
have all these crazy leaders, all over the world. And how is it now in Delhi?
see, I have to say it's a lot better than a couple of months ago. A lot better. You have to be careful. You cannot keep your guard down. The schools have just opened, like standards 9 to 12 only. And almost all organizations are open. Even movie theaters have opened, so everything has opened essentially. So in that sense, right now we are a little better off than what we were maybe a couple of months or 3 months ago.
So that's much better than Israel, actually.
No, that's what I was, kind of wondering how it is in Israel.
Yeah. Hopefully in a week or two, I don't know, maybe we will get back to a relatively normal situation, although it's not clear what this relatively normal means.
Yeah. So the normal now has a new definition, it seems.
Yeah, I guess so.
So I'll hand it over back to Soumik. Soumik, I think it's getting close to 4, right? So
Yeah.
so you can, Gilad, I'll come back to you and talk again later.
Okay.
Yep. Thanks again for your time, Gilad. Thank you very much.
Yeah, my pleasure.
Yeah, we'll wait for a couple more minutes before we start,
Okay.
so that more people might come in.
Hey, Gilad, a quick question. Are you still working on that protein adenylate kinase?
Yes, I am. Yes.
You are, okay.
You are interested in it?
We just started with this isoform of adenylate kinase, AK3L1.
Okay.
And we were doing some experiments, in presence of crowders and all. So we saw some interesting data. But it's very difficult to quantify exactly how it happens for crowders. Very difficult. I mean, you do not have a good trend.
What are you measuring?
So measuring, starting with enzymatic activity. And then moving on to domain movements using FRET, like what you have done, but at the ensemble level.
I see.
And then trying to do some, solvation, looking at the protein matrix rigidity and so on.
And what crowders are you using?
It's these synthetic ones like Fecol, Dextran, PEG. These are the ones we're using.
Yeah. We've done a lot of work on crowding, I think 10 years ago or something like that.
You also had a paper or maybe a couple of papers with Gordon Schreiber, right? On that overlap concentration.
Yes. I had a project together with him.
Okay.
We had a joint PhD student at that time. We worked on protein association on the crowding conditions.
Yes.
Yeah.
Right.
But adenylate kinase could be indeed an interesting target for crowding experiments because it's very sensitive to what happens around it. Like, for example, if you add small concentrations of urea,
right,
the enzymatic activity goes up.
Okay.
Which is kind of counterintuitive. And then it of course goes down eventually, but in the beginning it goes up. So, and we are studying this now, and some interesting observations from that. Yeah.
No, even your paper on AK3L1 in Nature Communications, right? You had talked about a lot of these substrates and so on, right? The hierarchy essentially.
Yes. That was folding. Yeah.
Yeah, that was folding, right? That was folding. Yeah. Yep.
Right.
So we have seen that the Fecol itself, stands out amongst all the crowders.
In what sense?
It gives its maximum activity at 100 grams per liter, and then when you go to the other side, it decreases. So beyond 100, it decreases.
I see. So maybe it has some specific interactions with the protein.
I'm sure it has, but I've not done it with this protein, but you'll be surprised, Gilad, when I would go and do some ITC studies with these Fecol and so on, I would not get much, good data out of it. It means that it's like, somebody said about these quinary interactions and so on. People have talked about in terms of the crowding, like the soft interactions and so on.
Yes.
I think these are very transient in nature, but still, I'm not too sure how to quantify this exactly.
I see. So you don't see these interactions?
No, not really.
Interesting.
Yeah, very interesting.
Yeah. Obviously, we still don't understand crowding so well, I think.
At least I do not. I mean, that's what I've been trying.
Yeah.
Okay, we'll talk about it later, I think. Yeah. We'll get back to the seminar. Sorry. Soumik, over to you.
Yeah, sure. Okay, probably we can start. So I'll kind of start now. Okay, so hello everyone. So welcome to the Department of Chemistry, IIT Delhi. Okay, and hope you all had a great start to the new year, and thank you very much for joining this webinar today. My name is Soumik Siddhanta, and I'm the webinar facilitator and an assistant professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is a part of online Pratidhwani series, which the department is organizing since the last couple of months. The webinar series is sponsored by Author Cafe. Author Cafe is an online platform that aids with writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with products like Mendeley, Zotero, Orchid, Crossref, and so on. So you can think it of like Google Docs, specially designed and developed for the academic community, and much more. So before we start, I request you to please not unmute yourself during the talk. If you have any questions, please type them in the chat box and we will try to get at least some of them through to the speaker after the talk. So today we are thrilled to have Professor Gilad Haran from Weizmann Institute of Science, Israel. So born in Holon, Israel, Professor Haran earned a Bachelor of Medical Science from Hebrew University of Jerusalem School of Medicine in 1986. He completed his graduate studies at the Weizmann Institute of Science and received his PhD in 1993. Following postdoctoral research at the University of Pennsylvania, he returned to the Weizmann Institute in 1998 and joined the staff of his Department of Chemical Physics. He is currently the incumbent of the Hilda Pomeraniec Memorial Professorial Chair. Professor Haran's research focuses on the dynamics of individual molecules. Using modern laser techniques, he studies the relationship between the motion of molecules and their function. Clarifying the underpinnings of molecular activity is particularly relevant in biophysics, where scientists study how single molecule assembles to form working molecular machines. Other topics of research include enzyme dynamics, super resolution microscopy of T cells, and single molecular Raman scattering as a probe of plasmonic structures. Professor Haran has held several important positions at the Weizmann Institute, including Director of the Board of Studies in Chemistry and Director of the Solo Dweck and Maurizio Dweck Research School of Chemical Science. In 2011 and 12, he served as the chair of the National Committee of Israel Science Foundation to the IUPAB, International Union for Pure and Applied Biophysics. He was Dean of the Faculty of Chemistry between 2012 and 2018. Professor Haran is also a recipient of 2017 Advanced Grant from the European Research Council. He was awarded the 2017 Weizmann Prize and the 2019 ACS Physical Chemistry Division Award. So a very warm welcome, and over to you, Professor Haran.
Okay, thank you very much. It's a pleasure to have this virtual visit. As I told Soumik in the beginning, it would be much better to have an in-person visit, but that's what we have right now, and I hope to come back for a real visit sometime in the future. So today I'm going to share with you some research that has been done in my lab for several years now, in which we study the coupling of individual emitters with plasmonic cavities. And no worries, I'm going to explain what plasmonic cavities are, and I'm going to try to build the story step by step so that you understand what we're talking about, why this is important, and what we can learn. The research is really basic in shape, but still there are some issues that might be also interesting in the future for various applications, and I will mention here and there these issues. So starting with surface plasmons, for those of you who are not familiar, it's really nice to start discussing surface plasmons by looking at this cup from the Roman time, from the 4th century. It's called the Lycurgus cup, after the place where it was found. And you can see that if you illuminate it from the front, it looks kind of dull and greenish. But if you illuminate it from the back, like on the right, suddenly it has a very nice red color very bright, very beautiful. And the question is, why is that? And this is related to surface plasmons because the glass that this cup is made of is doped with metallic particles. And these metallic particles have excitations that are called surface plasmons. These excitations scatter the light. And so when you illuminate from the back, the light is scattered, and the light that goes to the front is only the red light. So what are these surface plasmons? So here's a small metallic particle in this cartoon, and when you shine light on this metallic particle, you separate charges inside the particle so that negative charges are on one side, positive charges on the other side, and they then oscillate with the light. This leads to scattering of light. This is something that is related to the common misscattering. You might have heard the term. A theory developed by Gustav Mie many years ago that explains the scattering of small particles. But in this lecture, we are actually going to focus on what happens near the surface of the particles rather than the far field, rather than the scattering of light to the far field. So next to the metallic sphere, we can calculate how the electric field would look like. And this is an expression for the electric field at the surface. And you can see that the electric field will depend on the impinging field, but also on the relation between the dielectric function of the metal and the dielectric function of the medium surrounding the particle. So since in the denominator there's epsilon plus 2 epsilon m of the medium, then if this epsilon of the metal can be said to be negative, we can have a resonance here because the denominator can be close to 0. So this is indeed the case for some metals, like silver, for example, around 360 nanometer. The real part of epsilon is exactly canceling twice the epsilon of the environment in the case of air, and we would get a resonance at these wavelengths. So this is the hallmark of surface plasmons. And in fact, if we have two particles together, their resonances can couple together, and then the electric field becomes inhomogeneous, and it becomes strongest at the gap between the two particles. And this is a very interesting situation because you can see it here in this calculation. You can see how the field becomes very strong in the middle, and this really looks like a cavity. And we are going to discuss from now on this situation as a situation by which we have a plasmonic cavity, and we are going to study what happens when we do various things inside the plasmonic cavity.
Like 2 days back, there were two students, Pragati and Sastine, who had come to office. So
it sounds like somebody has not muted his microphone.
Yeah, I muted them now. You can continue.
Okay.
Sorry for the.
Yes. Okay. So here's the situation again, two particles, and now we start putting stuff in the middle. And the first thing that everybody wants to put there is molecules. Actually, the rest of the talk, we are not going to talk about molecules, but imagine that you have a molecule there. So what happens is that because of the strong electric field, electromagnetic field in the middle, you get strong scattering, strong Raman scattering, and this is the basis for what is called surface-enhanced Raman spectroscopy, or SERS. Here's an example of a spectrum of a single molecule in the gap between two particles. But we really want to go and talk about one specific brand of these plasmonic cavities, or sometimes called antennas, because they scatter light to the far field. And these are cavities that are made of, that look like bow ties, that are made of two triangles like this arrangement here. And I forgot to put here the dimensions, so you can see that the dimensions of this particular structure made by electron beam lithography are about 80 nanometers across here, so, and about 150 nanometers in this direction. So we, as before, we have two particles, and when we shine light on them, there is a strong interaction between the surface plasmons in the two particles, and then we can have a situation where we have a strong field in the middle. And you can imagine this in terms of the arrangement of the charges in the two particles, like I show here. Now, this arrangement, where we have the two particles, dipoles that are aligned together, This is called the bright mode because it emits light to the far field. But we can also have another situation where the two modes, the two dipoles are pointing towards each other, like here. And then if you sum these two dipoles, of course, you get zero. This means this is a dark mode. It cannot emit to the far field. But we will see that we can still do some interesting physics with this dark mode. And you will have to bear with me with regard to this dark mode. As they say in the theater, a gun that is seen in the first act is going to fire in the last act. So wait till the last part of the talk to hear about the dark mode. But in both the bright and the dark mode, if we look on the electric field distribution in the gap, we see that there is a strong electric field there. It's not uniform. Sometimes it's closer, it's stronger close to the particles themselves, but in any case, it's very strong in the gap, and that's what we want to actually use for our studies. So in the rest of the talk, we are going to talk about how we couple plasmonic cavities and single quantum emitters. So we want to put quantum emitters in this gap and couple them. This is work that was started in my lab several years ago by Dr. Santosh Kotny, who is already back in India. And then it was continued by Drs. Ora Biton, the head of our nanofabrication unit, Dr. Satyendra Gupta, who is now finishing his postdoc in my lab and is starting to look for jobs. So if you see his application, look at it very closely because he's an excellent guy. And Dr. Lev Chuntonov from the Technion, who is our very close collaborator. So let's talk about cavities for a moment, more generally than plasmonic cavities. So in a field of physics called cavity quantum electrodynamics, cavity QED, people look at individual quantum emitters inside cavities. Usually they use dielectric cavities. Let's imagine just two mirrors, and in the middle we have a particle. So the particle can couple to the mode of the cavity. And so you imagine here that you have this cavity mode and the excited state of the particle, and they couple together. And because of this coupling, we get two new levels that are separated exactly by twice the coupling strengths. And this splitting between the two new levels leads to a split spectrum. So if we have here the spectrum of the emitter and the spectrum of the cavity, then together we get this new spectrum, and we have this dip in the spectrum that we can observe. I'll show you an example from an experiment in a minute. And this is a phenomenon which is called vacuum Rabi splitting because it can occur even in the absence of photons in the cavity. Just the vacuum mode of the cavity couples to the particle and leads to splitting of the spectrum. Now, there are many applications of ideas like this one of coupling an emitter to a cavity. Some of them are researched by physicists in relation to quantum information processing, and some of them are actually researched in a field that started perhaps more recently in chemistry, and this is the ability to actually influence chemical reactivity by strongly coupling chemical reactions into within a cavity like this one. We are not going to talk about either of these applications. As I said, this is a fundamental research talk, but we are going to talk about what happens when we put quantum emitters inside plasmonic cavities. But let's first look at one example from the literature of a dielectric cavity. This is a photonic crystal, and inside this photonic crystal, one can put a quantum emitter. The advantage of such a cavity is that it has what is called a very high quality factor. The quality factor determines how many times a photon that is trapped in the cavity will bounce back and forth before it escapes. So in a cavity like this one, there will be many bounces of the photon before it escapes. And because of that, there is a possibility for coupling to a quantum emitter. And you see here the spectrum of an emitter, and you see the vacuum Rabi splitting that I mentioned before. You should notice that the spectrum is very narrow. This is because everything here is done at very low temperature with a very high precision laser system, and this requires very specialized equipment. The question is, can we do the same at room temperature with a regular laser under very mild conditions? The answer is yes, if we use plasmonic cavities. We are back to this situation where we have two plasmonic particles and the gap between them. We will go back to the bow ties in a minute. This is just a cartoon to show what happens. And what happens is quite interesting, because on the one hand, the quality factor of plasmonic cavities turns out to be much, much worse than the quality factors of the electric cavities. And this is because metal particles are actually absorbing some of the light. So these particles lead to losses, and they lead to a much smaller quality factors. In other words, a photon will bounce a much smaller number of times in such a cavity. On the other hand, the volume here in the gap is much smaller than the volume inside the dielectric cavities, where it is limited by the diffraction of light. So here we can get a volume which is significantly smaller by maybe 4 or 5 orders of magnitude than the volume in dielectric cavities. And this leads to what we call a high figure of merit. Q over V is much higher, can be much higher than in the electric cavity. And this might lead to strong coupling between an emitter and the cavity, even at room temperature, and even with a very broad spectrum that characterizes a plasmonic system. So let's see how it works. We are going to use for our emitters colloidal quantum dots. Colloidal quantum dots are made in solution by chemical methods. Their advantage is that they have larger oscillator strengths than molecules, and they are also more photostable than molecules, so we can do longer experiments with them. But another advantage for our experiments is that they can actually be directly observed in the electron microscope, which molecules cannot. And that means that we can actually count the number of quantum dots inside our plasmonic cavities. And let me show you how it works. These are several examples of plasmonic bow ties with quantum dot inside, and the red arrows point to the quantum dots. We control the number of quantum dots to a certain extent, but not completely. So we need to know after the experiment how many quantum dots we had in each cavity. Of course, we prepare many of these cavities. So sometimes we have one, sometimes we have quite a few, like here, sometimes we have two. And this we can count after we do the spectroscopy. So when we do the spectroscopy, we see significant dips in the spectrum, which are indicative of the coupling that I mentioned before. So you can see that in this case, there are what we think are 2 particles, and you see a big dip. Here there are 3 particles, again, a significant dip. And sometimes, even when we have a single particle, we get a dip in the spectrum. Sometimes there is no clear dip, but only a slight increase in the width of the spectrum when there is a single particle. But overall, we can see this phenomenon of coupling between individual quantum dots, or a very small number of them, and the cavity. Now, how do we prove that this is indeed, that the gap, that the dip in the spectrum is indeed due to strong coupling? We can prove that by using the polarization of light. So obviously, as I mentioned before, the mode of the plasmonic cavity that would couple to the particles would be the mode along the direction of the 2 bow ties, the 2 bow tie parts. And so we can turn the illumination to be polarized along this direction, or turn it to be polarized along the orthogonal direction, and see the effect. So this is what I show you here. We start with the polarization along the bow tie, and you see the dip. But as we change the angle gradually to 90 degrees, we lose this dip. And this is a direct proof that the dip is due to strong coupling between the plasmonic mode, the cavity mode, and the particles. So what I showed you here is that plasmonic bow ties can form cavities with a high figure of merit. We can couple quantum dots that we insert into these cavities, and we can see strong coupling that can be achieved even in the limit of a single quantum dot. And the advantage of the quantum dots inside the cavities, as I mentioned, is that we can actually go to the electron microscope and count them. Okay, so far, what I didn't mention perhaps is that the spectrum that I showed you before is a scattering spectrum. We looked at light scattering from the plasmonic cavities. But we wanted to know whether there are other ways of looking at the strong coupling besides light scattering. And one natural way is photoluminescence, because when we excite the quantum dots, and here I plot the levels of the quantum dots, the valence band, the conduction band, and when we couple it to the plasmon, we have two split polaritonic levels, as we call them, and we can have photoluminescence from both the high energy polariton and the low energy polariton, and we should expect a splitting in the spectrum just as we did for the scattering. Is that what happens? So Dr. Satyendra Gupta in the lab started to do experiments on similar systems to the ones that I just showed you, but now instead of just looking at scattering, he also looked at photoluminescence. So here's an example of one such system. We have here two particles, two quantum dots, and you can see the scattering spectrum with a clear dip indicative of vacuum Rabi splitting. And here's the photoluminescence spectrum from the same device, again showing a dip in the spectrum. So we were quite happy in the beginning because we thought, wow, yeah, we do see the splitting in the photoluminescence spectrum. But then Satyendra actually overlapped the two spectra together, and then we started becoming quite puzzled because what we saw was that the PL spectrum is much narrower than the scattering spectrum in orange. And in fact, it's even more puzzling because we could actually quantify the splitting in each of these spectra, and we expected that if they are both split because of the coupling to the cavity, then there should be a correlation between the splitting in the two spectra, even if one of them is narrower than the other. So here's a correlation plot, and you can see that the splitting in the PL spectrum, in the photoluminescence spectrum, does not at all depend on the splitting in the scattering spectrum. So that was even more puzzling, and we decided to turn to another experiment in order to probe the quantum nature of the emission from these cavities. And there's a famous experiment that is called the Hanbury, Brown, and Twiss experiment, in which you split the photons that come from an emitter into two detectors, and you look for coincidence between the arrival of photons on the two detectors. And if there is a single quantum emitter that you look at, there is a phenomenon called anti-bunching, which means that two photons cannot be emitted at the same time by this emitter, and that's why we will not see a coincidence count at time zero that indicates two photons arrived separately at the two detectors. So here's how it's going to look like. This is the what we call the second order correlation function. We see that at time zero, the probability to get two photons, which is what this correlation function measures, this probability is very close to zero. It's not quite zero because of background and so on, but it's very close to zero. In fact, there is an expression that tells us the relation between the probability at time zero, between the value of this function at time zero, and the number of particles that we look at. So if we have a single particle, you can quickly calculate that this is going to be zero. But if we have two particles, we expect G2 at time zero to be larger than zero. And if we have, let's say, three particles, here's what we get. So you see that G20 becomes much larger, but there is still a dip here, but this dip corresponds to what we expect for three particles. So this experiment actually gives us another way to count the number of particles in our cavities. And in fact, we did this exercise and we compared what we get from the dip in the correlation functions to what we see by the electron microscope, and we have a fairly good agreement between the two measurements. But we are more interested now in the properties of these quantum emitters inside the cavity. And besides the fact that we now know that we can actually have a single quantum emitter, also in the quantum optic sense, that it emits as a single quantum emitter, we also wanted to understand what happens to the lifetime of these emitters. So actually, the decay of the correlation function tells us about the lifetime of the emission of the quantum dot. And so this is a quantum dot on glass, not within a cavity. And you see that the lifetime here, we measure it to be between 20 to 25 nanoseconds. There is a distribution of lifetimes between different quantum dots, but that's the range. On the other hand, when we put the quantum dot inside the cavity, we get a lifetime of about 10 to 11 nanoseconds. So that's quite puzzling again, because we expected that the coupling to the cavity, the strong coupling to the cavity, would shorten the lifetime much more, because the quantum dot should inherit partially the properties of the plasmon, and the plasmon itself decays on the femtosecond timescale. So why is the lifetime so long here? So we have three puzzles that I already mentioned. First of all, the photoluminescence line is too narrow compared to the scattering line. The photoluminescence splitting is independent of scattering, and the photoluminescence lifetime is too long. So in order to understand, or in order to solve the conundrum behind these three puzzles, we looked at the literature and we remembered that quantum dots actually have quite coupled excited state structures, and one of the excitations that are quite familiar in quantum dots are charge traps on the surface of the quantum dots. In other words, an electron can be trapped on the surface and remain there for a long time, and that would lead to what is called a dark state, a dark surface state of the quantum dot. And this dark state would emit, but it would emit with a very, very long, you can see it here, very long emission time, very long lifetime of the order of maybe even microsecond to a millisecond. And that's why it's actually called a dark state, because it's difficult to see it under regular conditions. So perhaps what we have here in our experiment is the involvement of such a dark state in the excited state dynamics that contributes to the photoluminescence. In order to see if that's the case, we turned to my good friend and colleague from San Sebastian in Spain, Javier Ezpurua, and his colleagues, especially Thomas Neumann, who was a PhD student in his lab. And Thomas started doing some calculations on the system that we have been working on. So he imagined the following model for the system. Here's the quantum dot now, and instead of having just a single bright excited state, it has another dark excited state, which is slightly lower in energy than the bright state. And both of them can emit, but of course, when we just look at the quantum dot, the bare quantum dot, not inside the cavity, we expect the emission from the dark state to be much, much weaker than the emission from the bright state. And in fact, in the model, there is a factor of 1,000 or 10,000 between the emission rates from the two states. Then we have the cavity as well. So the cavity also generates a mode. This is the plasmonic mode that we already discussed before. And this mode can now couple to the quantum emitter. And now we have the full model, and we can solve it on the computer. So this is what Thomas did. He solved this model using the quantum mechanical equations that correspond to the model. And then he could calculate various properties, like various spectra of the combined system. So first of all, the scattering spectrum, and you can see the strong dip in the scattering spectrum that indicates the same behavior that we see in the experiment, where we see the vacuum rabbit splitting in the spectrum. Then the PL. So the PL looks indeed narrower than the scattering spectrum, and it still has this bilobed structure. But now Thomas could come and tell us that, hey, actually this lower energy peak in the spectrum is just due to the dark state in the model. And so we asked Thomas, how do you know that? And he said, well, that's easy to do in the simulation. You cannot do it in the experiment, but I can do it in the simulation. Remember that in the model, there are two couplings, one for the bright mode and one for the dark mode. So I can turn off the coupling for the dark mode completely. And you see that in that case, the spectrum does not show the two peaks anymore. It shows only a single peak. The yellow spectrum or orange spectrum here shows a single broad peak, which is due to the coupling of the bright mode to the cavity. But what happens here is that, in fact, inside the cavity, the dark mode also couples, and it becomes bright due to the interaction with the plasmonic mode, and that's why it appears in the spectrum. So this solves at least part of the puzzles that we saw in the experiment. There is one more puzzle that we can solve now by calculating the correlation function, the second order correlation function from the simulation. And you can see here that, in fact, the correlation function has two parts in it. One is a very fast part. I don't have here an enlargement of this part of the correlation function, but you will believe me that this is actually in the femtosecond, on the femtosecond time scale, and this is due to the bright state. On the other hand, there is a slower part which is due to the dark state. So that explains what we see in the experiment, because in our experiment, we do not have the time resolution to see the femtosecond part of the correlation function, only the slower part. And so what we see in this G2 or correlation experiment is only the correlation in the emission due to the dark state. So that explains also the last conundrum in the experiment, which is what we see in the correlation function. So altogether, what we find here is that the emission features can be attributed to a very interesting but very complex interaction between the excited states of the quantum dot and the cavity. It's not only the bright state that couples to the cavity, but also the dark state, which becomes bright then. And this leads to a very interesting behavior that we can actually decipher by combining this quantum mechanical calculation with the experiment and the different observations that we have in the experiment. Okay, so now we move to the last part of the talk, and we were still thinking how we can observe the strong coupling using other types of experiments, other observations. And in particular, we were interested in this dark mode that I mentioned in the beginning of the talk, the dark mode now not of the quantum dot, but the dark mode of the plasmonic cavity. And remember that I said that we are going to go back to that dark mode. So this is where we are coming back to it. And you see here again, the two dipoles in the two parts of the plasmonic cavity are pointing towards each other. So the total dipole is zero, meaning there is no far field emission, but there is still a way to probe this mode, not in the far field, but in the near field. So what does it mean? It means that we need to couple locally to this mode by doing some experiment. So one experiment that can be done is an experiment called electron energy loss spectroscopy. In our institute, we have a very nice electron microscope that can do this experiment with high spectral resolution. And Dr. Lothar Huben is the person who runs this microscope, runs this facility, and he was our collaborator on this experiment. So here the idea is the following. You shine a tight focused electron beam in the electron microscope on the sample. And the electron beam can couple to different excitations in the sample, including to the plasmonic excitation. And due to this coupling, it loses energy. And therefore, the electrons that pass through the sample have lower energy than the electrons that we started with. And we can actually use a spectrograph to look at the spectrum of the electrons. And this is called the electron energy loss spectrum. And it tells us about the various excitations of the spectrum. And here we are focusing, as I said, on the plasmonic excitations of the particle. And the nice thing about this method is that it is a local method. In other words, we can move the electron beam to different points along the sample, and we can get the excitation of the plasmon at different points. For example, for this particular triangle that is shown here, here is the EELS map, and you can see that the EELS is strongest at the corner of the three different corners of the triangle. Okay, so let's see what happens when we do this kind of experiment on our bow ties. You can see it here. These are different maps at different energies. We can map the surface at different electron energy losses. And we can see that for each energy range, we get a different spatial map of the excitation. So that means that we are actually coupling to different modes of the bow ties. And we can look at each of these maps, in fact, and I'm not going to do that because of the lack of time, and we can assign it to a different mode. We are going to be focusing only on the two modes that we already discussed, which are the lowest energy bright and dark mode, and we are going to look at these two. So here's the bright mode first, since we are most familiar with the bright mode. Let's first start with that one. Again, this is the distribution of charges inside the two particles, and you can couple well to this mode by putting, actually, this is a bit counterintuitive, putting the electron beam not at the center, but at the corner of one of the triangles. So if you do that, you can see that, this is a calculated charge distribution inside the particle, and it looks like, indeed, the two dipoles aligned parallel to each other, like I showed you before. This is the overall spectrum that we get at this point. And if we look at close to the peak of this spectrum, the first peak, lowest energy peak, this is the map that we get. So this is the peak of the bright mode that we're talking about. Now, what happens if we put quantum dots inside the gap here and repeat this experiment? So here's a bow tie with quantum dots, and we put the electron beam here at the corner, and lo and behold, we get splitting in the spectrum, but now it's the EELS spectrum, so that's quite nice. We can quantitate the splitting, and it seems to be quite similar to the splitting that we get in the scattering spectrum, so we were quite happy to see that. And then, of course, we move to the dark mode, and the dark mode, as I said, cannot emit at all to the far field, but we can excite it with the electron beam, and the best place to excite it turns out to be the gap between the two particles. And so we put the electron beam here, and this is the calculations that shows how the charge distribution in the particles would look like, two dipoles pointing towards each other, as you remember, and this is the map of the mode, so that you can see that indeed that's the best place to excite it, and the spectrum of this mode. So this mode, as opposed to the bright mode, it peaks at a slightly higher energy, around 2 or 2.1 electron volts. And so we decided to take quantum dots that actually have a resonance at this particular frequency and put them into the cavity and see what the effect is. And so here is the electron microscope image of the system. These are the quantum dots here. They have a resonance at 1.99 electron volts, and we put the electron beam in the gap. And again, we get a splitting in the spectrum. So what we see here is that the quantum dots that we picked up in this case, that are in resonance with the dark mode, are actually also leading to a strong enough coupling to show splitting in the spectrum. Now, there is an interesting observation that you can make here, which is that if you look closely on this map from the electron microscope, you can see that the particles are actually not quite inside the gap, but they are in the periphery of the gap. And this can be rationalized by looking at the distribution of the electromagnetic field of the dark mode within the gap of the plasmonic cavity. And this is the calculation here. And you can see that, in fact, the dark mode is strongest not at the center, but at the periphery of the dark mode, of the cavity. So that explains why, if we put the particles at the periphery of the cavity, we are going to get a good splitting in the spectrum. And this is what I show you here from a calculation, but it's very similar to what we get in the experiment. So to close this part of the talk, what I showed you here is that we can use also electrons in the electron microscope in order to couple to our plasmonic cavities and to show this phenomenon of strong coupling between quantum emitters and the cavity. In this case, the added value is that we can look at the dark mode, not only a bright mode, because all the other experiments like scattering and photoluminescence can only observe bright modes. And we can also, in fact, map the distribution of the coupling as a function of position in the sample, which I didn't show you here, but this can be done for the different modes, and we can see exactly what happens there, and we can understand better the arrangement of this plasmonic mode and how it couples to the emitters. Finally, to wrap up the whole talk, what I showed you here is that we can create these plasmonic cavities made of bow ties. We can put quantum emitters inside. Our favorite quantum emitters are quantum dots, and we can use several different methods in order to couple, to look at the coupling between the quantum dots and the plasmonic cavities. We can use light scattering or photoluminescence or EELS spectroscopy, and in each case we can see interesting phenomena that have to do with the different modes of either the cavity or the emitter, and we can characterize them by a combination of experiment and theoretical analysis. In future work, we hope to be able to improve the coupling and make it even larger so that it will be easier to probe these phenomena, and then to study coherent interactions between different quantum dots induced by the cavity. Imagine that you have exactly two quantum dots inside the cavity, and they both couple to the cavity and to each other indirectly through the cavity. We would like to understand how this works and what we can learn from that about coherence between quantum emitters. Finally, I would like to thank my group. I already mentioned the people who were involved in the plasmonic research in the group, but there are many other people who are doing actually single molecule biophysics, and I did not mention their name, of course, and I would like to also thank our collaborators, both the collaborators in Spain, whom I already mentioned, and collaborators in the Czech Republic, in Brno, Michal Kvapil, Vlastimil Kropik, and Thomas Sikola, and these are the sources of money relevant for this work, and thank you very much for listening. I will be glad to answer questions now.
Thank you, Professor Haran, for the wonderful, insightful, and stimulating talk. So, any questions? Like, are you ready to take questions now, Professor Haran?
Yes, of course.
Okay. So, any questions for Professor Haran? Okay. So, yeah, you can either raise your hand or type in your questions here. So we can have in-person questions also. So we are also live on YouTube. So sometimes we do have some questions from there too. Okay. Okay. So yeah.
Shomi, can I go ahead and ask Gilad?
Please. Yeah. Please. Yeah.
Hi, Gilad. Promith here again.
Yes.
Yeah. Thanks for the wonderful talk. A couple of, kind of more of sort of incursions that I would ask you about is these interactions between the dark mode and the bright mode, and you look about it in a futuristic manner. How would you think about having these interactions in a meaningful manner do something for you in terms of the quantum dot emitter? That means, what properties do you think you can control, apart obviously from the lifetime, in terms of reactivity or something like that, do you think?
So that's an interesting question. We actually thought a little bit about this question. We don't really have a very sharp answer. But one answer would be that actually some people in the quantum information field are interested in dark modes because they can store information for much longer times than bright modes. So if you can actually somehow control how much of your excitation is in the dark mode versus the bright mode, which we do not control right now, but imagine that you could, by using perhaps pulsed excitations, you could control that, then that would allow you to actually control better the overall lifetime of the quantum emitter in the cavity. And by turning on and off perhaps the coupling to the cavity, you can control whether the dark mode is dark or bright, and that will allow you an extra handle on what is going on there. and how to control it. But these are all, as you said, futuristic ideas that we don't have a good experiment that we can tomorrow try to do on this, but perhaps in the future we will be able. Yes.
Okay. So thanks. Second point from my side is, what about not using quantum dots, but using like single molecule emitters and try to couple the respective vibrational modes with these plasmonic ones? Is that possible? And to control the chemical reactivity?
So regarding vibrations, you might know that there is a group of researchers that basically started in the lab of Thomas Ebbesen in Strasbourg, and actually there is even one person, Gino George, who moved back to India and is very successful with this idea of coupling vibrations of molecules to cavities. In this case, these are not plasmonic cavities. The reason is that the coupling, because vibrations have a very weak dipole moment,
Right.
then their coupling to the cavity would be very weak. So it's going to be extremely difficult to see a single molecule through its vibrational coupling to a cavity. On the other hand, if you have many, many molecules, the coupling builds up because of all these molecules, and you can get coupling that you can see by having an Avogadro's number of molecules. So all these experiments that are done inside cavities are done in the limit of many molecules. It would be interesting to try to at least downscale this. Imagine that you have perhaps not Avogadro numbers of molecules, and on the other hand, perhaps not 1 or 2 or 3 molecules, but thousands or many thousands of molecules inside a small gap between plasmonic particles. Will we be able to see coupling then on the vibration side? I don't know. That could be an interesting experiment to try.
Okay. Thanks again, Gilad. I'm done, Shomik.
Okay. So there is one more question. So the question is, so what is the what happens when the plasmonic bow ties, when you make the edges really very narrow? Is there an effect on the coupling in that case?
Yes, in principle, the narrower the gap, the narrower the edge, the better it is. But there are limitations due to the fabrication process. So what you saw is more or less our best in terms of what we can achieve with fabrication. There are other techniques. We use electron beam lithography. There are other techniques that allow perhaps sharper corners. We haven't tried that yet because we don't have that instrument here. It's in a different university in Israel. So we haven't tried it. It could contribute to a stronger coupling, but we need to try it.
Okay. And also, like, is there any effect of the environment? For example, if you do it in a liquid, or
yes, definitely, because the refractive index of the environment or the dielectric constant of the environment is very important for determining the exact position of the various resonances in the system. So you might, of course, the strong coupling between the cavity and the emitter is strongest when both of them are on resonance with each other. And so you might imagine a situation where you change the resonance of the cavity by, let's say, adding to the environment, let's say, adding a liquid with a high refractive index, which shifts the cavity resonance momentarily, and that removes the coupling with the emitter inside the cavity. And then when you remove that liquid, you're going to get the coupling again, so you can get some kind of an actuator like that. That's an idea that I know that some people are actually attempting to do something like that. And it indeed builds on the fact that plasmons are quite sensitive to the environment.
okay. So the next question here is, so what can be the probable applications of this kind of coupling? Probably means by like some real application of this kind of nanostructures and coupling.
So I have to point out, I will tell you about a few applications, but I have to point out that we are actually, my lab typically is more interested in the fundamental physics, trying to understand really how we can learn some new physics. And we think that by doing these quantum optical experiments at room temperature with these plasmonic systems, we can actually learn a lot of new physics that one cannot learn in other systems. But there are, as I said, there are the applications. There should be various applications in quantum informations, like, for example, single photon sources. The people in physics are very interested in building sources that emit exactly a single photon and exactly or a stream of exactly identical single photons. That's very difficult. We might be able in the future to see if the plasmonic cavities might help with that. We don't know yet. So that's one possibility. Another possibility is, as was mentioned in my answer to Pramit, to try to see if we can actually use the small gap in plasmonic cavities to influence chemical reactivity in molecules. Here, as I said, it's not going to be a single molecule experiment, but still we are going to employ the small gap in order to get strong interaction. So that's a more chemistry application. I mentioned also a more physicsy type of application, but obviously there are ways to think about applications here too.
Okay. So any more questions from the audience? Okay, so I see a lot of students here from our department who are pursuing their masters or probably bachelors. So any suggestions to them, for their journey in science from your side?
So my best suggestion is always the same. Follow your heart. Do whatever you think is most exciting to you. Don't ever think in a political way. What will be good for my career? What field is more fashionable now? I should go to that field and do research. No, don't do that. Think about what excites you most and do that. And that's the best way to succeed in science. Do just whatever you're excited about.
Okay. I think those are some of the golden words. I think students will definitely benefit. So I don't see any more questions. So I think.
Somik, I just have one.
Yeah, sure. Sure.
Gilad, just last one from my side. So how did you kind of zero in on the use of these bow ties for this confinement?
So as usual, there is previous work. So people have used bow ties before, mostly in order to enhance the photoluminescence from molecules. So you might imagine that you put on top of the bow ties, you put a liquid with emitting molecules, and from time to time, one of these molecules is passing through the gap, and then it benefits from the strong field in the gap, and it emits light more often than when it would emit just in solution. And people use that, and they show that you can get an enhancement of the emission even by a factor of 1,000 from bow ties. And so we've read this kind of work over the years, and then when we decided to do some work on strong coupling, we thought that bow ties could be a natural candidate for that work because of the strong enhancement. And this is related to my answer to one of the first questions about the edges. So yes, because the bow ties have relatively sharp edges, they lead to strong coupling, and that's a benefit of the system that led to us choosing it for all these experiments.
Okay, thanks a lot, Gilad, for answering the questions.
Well, thank you.
Yep.
Okay, so I would like to thank you again for accepting our invitation and agreeing to give this webinar today. And I would also like to thank all the participants here for attending the talk, Professor Haran. And also, as I was saying before the talk, that once all this COVID crisis gets over, we'll definitely like to have you here in person someday.
Okay.
Yeah. And yeah, so thank you again. And
Okay.
hopefully
Thank
we'll
you
see
very much for the invitation, and hope to see you soon.
Yeah. See you.
Thanks a lot, Gilad. Thanks a lot for your time.
Thank you. Bye bye.
Bye bye.
Yeah.
Talk to
Bye-bye.
you later.